So, remind me, what did we say about this stuff on Friday?
Do a line. Yeah, the bottom one's 0.
Okay, yeah, okay, good. So the bottom one, if we're defining the, we don't know what the function f is, right? But we're told this much. We're told that if the definite integral of f of x dx from 0 to 8 equals 11, first of all, what does that statement mean in terms of a picture? That means what? What is equal to 11? Okay. Okay, good. So the area, if we make vertical slices at 0 and 8, if we slice that function at 0 and 8, all the area trapped underneath the curve between those vertical lines at 0 and 8 is equal to 11. If you summed all that area up, good. Now, this is a little odd. Explain to me how this could happen. How could the area under the function f of x from 6 to 8 equal negative 3? Good. Okay, if it dips below the negative axis, because we said that we were going to reckon area in calculus as being positive when it's above the x-axis and negative when it's below the x-axis, right? Okay. Then, what about this first one? Oh, and then we said, okay, down here, then the definite integral of f of x dx from 0 to 0. Now that's going to have to equal 0, as you said, because there is no width to that interval, so there can't be any area, right? So that one's got to be 0 for that reason. What about this top one up here? 3. Okay, it's positive 3. Now explain. Why is that positive 3?
Right to the left.
Okay, good. And there's the other thing we said about how we reckon area. We say it's positive from when it's above the x-axis, and we also, as we're sweeping out area from left to right, from lesser to greater values of x, that's considered to be positive. But if we add the area up backwards, if we're going, instead of going from x equals 6 to the right up to x equals 8, if we start at x equals 8 and we go to the left, back to x equals 6, that's the opposite negative direction. And so it's going to reverse the sign of that area. So even though this area is evidently below the x-axis and negative, if I add it up backwards, two negatives make positive, right? So it ends up being positive area. I'm going to go backwards. Okay. What about this guy here? What's the area going to be from 0 to 6? 14. Okay. Yeah, 14. It's got to be one of the two, 14 or 8, doesn't it? Now let's remember the property that allows us to do that. If this first area is defined from the lower limit of integration 0 to the upper limit 8, and the second one is defined from 6 to 8, well, those don't add properly. But if I flip this one around, what if I add these two together? That works, because look what happens then. I start at 0, I walk over to 8. With this limit right here, I start at 8, and I end up back at 6. Right? And so those two make sense to add together as definite integrals, because the finishing spot, the ending x value of the first integral, becomes the beginning of the second one. Okay, and we had a property we talked about on Friday that demonstrated that. We said that in general, the definite integral of f of x dx from a to c plus, remember this one? Yeah. The definite integral of f of x dx from c to b equals, yeah, the definite integral of f of x dx from a to b, because the c's, where we left off with the first area, we picked up with the second one, and so we just joined them together into one big area. Okay? Does it matter in this case that the second one went backwards? Doesn't make any difference. Okay, make sense? Mm-hmm. Okay. All right. So we got an answer here then of 11 plus 3 is 14. Okay, good. We said some other stuff too. We talked about how we can take, sometimes we can take definite integrals, and rather than having to do the complicated calculus stuff, being as we know that what they represent are areas under curves, sometimes we can just trade those areas for geometric areas that are easy to add up using formulas, like in this case. Right, what is this? If I look at this function, right here, if I were to graph that thing, think what that's saying. Well, now, the square root, or the absolute value of x is just a v, right? Just a v with slopes of 1 on the left and the right. Where's the vertex of the v? If I were to just graph, say, f of x equals absolute value of x, yeah, doesn't it just look like that? Right? Slope of 1 on the right, negative 1 on the left. Going back a couple years, remember dealing with those. Okay, so how am I going to transform that if I do this stuff to it? If I multiply it by negative 1, what's that going to do? That's going to flip it around the x-axis, right? So now the v is opening down. And then if I add 4 to that, isn't that just picking it up by 4? Right? And so we can really quickly get a good sketch of this, right? This is just going to look like like that, doesn't it? All right. And if I'm just adding up the area from negative 4 to positive 4, I'm just adding up all that area in there, right? That's easy enough. What's that area? Couldn't I just take this piece right here and just rotate it around and fill that in and make a square out of it? Right. So what is it? Yeah. So then wouldn't it just be 4 by 4? Yeah, it's just 16, right? Agreed? See how easy that is? So in some cases, we can do that stuff, right? We can take the argument of the definite integral, the integrand, and if we know what the shape of that curve is, sometimes it's easy just to find the area geometrically. Okay? We can avoid the calculus completely. Not that we don't love calculus, but we always want to take the easiest way we can. Now, we could probably do the same thing here, but I want to illustrate a different point with this. Sometimes when we're doing integrals of functions like, here's an example. It could also be like a piecewise function. We have a definite integral of another absolute value function. If we want to add this up, that's not going to fit one of our standard forms. And remember, let me just again remind you that the game we play in integral calculus as opposed to differential calculus, now that we're into this new stuff, the game gets a little more sophisticated. Now we don't have such simple rules to follow like we did with differentiation. With integration, we have to follow this set number of little patterns that we have. We don't have very many of them, right? I mean, we have that little list in the book, but we have six trig integrals, and we have a power integral, and we've got, we don't have much. We don't even have the equivalent of a quotient rule and a product rule, and things like that. We have very little to work with. And so the only way that we can do calculus, integral calculus right now, is if we can pre-write the function, the integrand, to look like those very few forms that we have, right? This one doesn't look anything like those at first, right? And so any suggestions what we could do with this? And ignoring the fact that we probably could make this one geometric, but we won't this time. We'll actually do calculus on this one. Any suggestions? And we've done stuff kind of like this before. Remember, it's been a while, but we did some derivatives involving absolute value functions. Did you remember what the trick was there? We don't really have standard forms for the derivatives either. Okay, we did something like that, right? We wanted to take that absolute value and turn it into, we wanted to trade it for a function without the absolute value bars, right? And I think the way we actually did it was we traded it for a piecewise function, right? Because remember that that the definition, a couple ways we can define absolute value of A. One of them is, what Jacob was saying is, the square root of A squared. Yeah, that's one way we can define functionally the absolute value of A. Okay, but the other way that we do this frequently, if we want to, a very useful way is to break it up into piecewise function, right? Because really, you know that there's two behaviors going on with an absolute value function. We go back to this previous page, and we have this absolute value function. It's doing one thing to the right of the vertex and another thing to the left of the vertex, right? And that can get more complicated, but typically that's the way it plays out. So we know that in general, the absolute value of A is equal to itself when A is positive, right? The absolute value of something positive is not changed. Remember talking about this stuff? And then its opposite whenever A is negative, and then it'd just be 0 when it's 0, right? So we could do something like that. We could take this function up here, this absolute value of 2x minus 1. Let's write that as a piecewise function. Okay, it's going to equal 2x minus 1 when 2x minus 1 is greater than 0, right? And it's going to equal the opposite of 2x minus 1 when 2x minus 1 is less than 0, right? And it would equal 0 in between when 2x minus 1 equals 0. Okay, now there's maybe a better way to write that, though. That's a little bit messy. Why don't we, these aren't very convenient ways of writing those inequalities. We would like those solved for x, because what we really want to know is, for what value of x are we transitioning between these two different lines, right? So we'll maybe do that one more time. The absolute value of 2x minus 1 then equals 2x minus 1. If I solve that for x, what do I get? If I solve this inequality, x is greater than 1/2. If I add 1 to this side and divide by 2. So when x is greater than 1/2, that's the value of the absolute value function, right? It's given to us by that equation. Okay, so then, now the algebra is going to be pretty redundant here. In each case, I'm just adding 1 and dividing by 2, only in this case the inequality sign is flipped. When x is less than 1/2, we get negative 2x plus 1. And then I get 0 at x equals 1/2, right? And so all I got to do then, if I want to do this integral, how am I going to restate that integral? If I want to add up the area from 0 to 2,
0 to 1/2. 2x minus 1.
okay, good. Does everybody see that? You see that when I'm adding this thing up, the area from 0 to 2, from 0 up to 1/2, I'm going to be down here, aren't I? Right? Because this is how the absolute value function is defined when x is less than 1/2, right? So on the interval from 0 to 1/2, I'm adding up the area under that line. Plus, the second area would be the area from 1/2 up to my upper limit of 2. And there I'm going to be adding up the area under that line. Make sense? Okay, so then our integral becomes color code these. So this is going to be the blue one. How about? And this will be the red one. Both of those are pretty simple. Okay, let's do this first one over here. What do we get if we anti-differentiate here? If we do the integral, what's the antiderivative of negative 2x dx? So we can just do that term by term, right? We got a plus sign. Okay, negative x squared plus x, good. And then, now, we won't put a constant here though, because remember we're doing definite interval. So we don't need the constant there, and we're going to evaluate that from 0 to 1/2, right? Okay, plus, what about over here? Okay, positive x squared minus x from 1/2 to 2. Right? Okay, and so if we finish this up then, if we evaluate this whole thing at 1/2, remember, that's how I have to do this. When I write this notation down, it's saying I'm going to evaluate the function at 1/2 minus whatever I get when I evaluate the function at 0. So it's the difference between those two, right? So we get minus 1/2 squared plus 1/2 minus, and at 0 everything's going to go away, right? That make sense? Okay. And then for the red stuff, same kind of thing. First I'll evaluate everything at 2. And then 1/2. Whatever I get from all that is my answer. So this gives me, what is that going to give me? 1/2 squared is 1/4, so we get negative 1/4 plus 1/2. It's just this whole thing, would you agree, just gives me 1/4?
Oh, yeah.
That make sense? Okay. Minus 0, right? So I just get 1/4 plus, let's see, 4 minus 2 is 2, minus negative 1/4. So I'm going to get 1/4 minus 1/2 there.
Yeah.
Minus negative 1/4. So 1/4 plus 2 plus 1/4. So 2.5 total.
Yeah.
We don't want to write it as a mixed number, so we'll write it as 5/2. Okay. Make sense? Okay. All right, last thing I want to show you for today. Mean value theorem. Now, the mean value theorem, this is a really easy one to conceptualize. This is another one of those examples of a picture theorem. Picture really tells the story here. Very useful theorem. What this tells us is that, and I'm not going to, the book gives you, it gives you a blue box with lots of words in it. Let's just talk about the gist of this and kind of get the idea conceptually what it means. The mean value theorem says that if we've got, first of all, we got to do all the fine print. If some function f of x is defined on the interval from a to b, so it makes sense, in other words, the problem makes sense, then the area under the function f of x dx from a to b is equivalent to some average value, and that's really what this f of c refers to, times the width of the interval. Okay? And so what you can think about us having done here, if we draw this picture, it's easy to kind of see what this means. Easy to see why f of c really does represent a very useful average value for the function on this interval. So let's say here's a and here's b. And if here are our vertical cuts that define the function, right, on that interval. And here's our original function. Let's say our function is doing something like that, but we're cutting it between a and b. So this is the only part that we care about in here, right? So we get some area under the curve here, right? Under this blue curve. only that area is, the value of the function changes quite a bit. Okay, but what if we were to take a two-dimensional calculus grinder and we were to come in here from above and grind this function into rubble from the top? And as we grind this thing up, the rubble's going to fall down the hill, and it's going to fill in the pit over here at the left side. Okay, see where I'm going with this? So if we do that, if we grind this thing down, eventually we're going to get to a point where we can't push the grinder down anymore because we're starting to run into the rubble, and we don't accomplish anything anymore, right? That, forgive the analogy, but you get the idea there. So if we do that, if I grind this thing down, at some point we're going to get down to this new level, probably right about there, where all this stuff up here has been ground down, and it fills in that little gap right there, right? At that point, the shape of the area is now a rectangle instead of this previously complicated shape, right? Okay, but the area is the same, agreed? Okay, so this is what we define as f of c. Okay, that's the average value of the function. Okay, it's the value. It's the value such that the area becomes rectangular instead of complicated. Okay, in other words, it's the value for which we could just multiply this height by the width of the interval and get back the area of the curve. Okay. Does that make sense why that would be an average? Another way you can think about it is, what if we were looking at this in terms of, say, distance and time? Right? What if this became a kinematics problem instead? What if we had so this is distance and this is time. Okay? And let's say here's our, what does that represent then, that trip? Okay, yeah, just constant acceleration, right? Speed is increasing. If this is distance on the vertical axis and time on the horizontal axis, then wouldn't the slope be the change in excuse me, it's not acceleration, what is it? Velocity, sorry. Wouldn't the slope be change in distance over change in time, which is just velocity, right? Okay, so this would represent, okay, what I really want to do is speed versus time, don't I? Never mind. Yeah, hang on. This is what I want. Speed versus time. That's what I want. Speed versus time. Now, what's the slope represent? Change in velocity over change in time would be acceleration. Good. So constant acceleration. Now, those of you physics types, you know what is the area? This is kind of a cool thing. What does the area under a velocity time graph represent? You guys talked about this? This is good stuff. Really good stuff. Oh, this is really good stuff. You're going to like this. Get this. The area under a velocity time graph represents displacement. How about that? So yet another reason that this integral calculus stuff, you can kind of see how this takes what we previously have with physics and just explodes it. We get all this new capability now. And so, which, by the way, we'll come right back to this. That allows us to do some really cool stuff. What about things like, this is just so cool. So what if we've got something like this? Say this is our velocity and that's our time. Now, what does it mean to have positive velocity? Just means what? Assuming we're just traveling on a line, positive velocity means I'm going in the positive direction, right? Negative velocity just means negative direction, right? Okay. And so if I did something like this, what really happened there? Well, I started with no speed. I accelerated. I went up to some maximum. That's when I hit my maximum positive velocity. I started to lose some of my speed. What happened right there? Okay. Okay, good. Makes sense? And then now I'm changing direction, coming back a little bit, and then I stop, right? And so if I add up the area under this curve, this is positive area. Whoops. Right? This is negative area. Makes sense, because I was going backwards there, right?
In the bottom, you're still accelerating, you're just accelerating in the other direction.
Yeah, exactly. Yeah. It's just negative acceleration. Right. And then, so what's my net result? Well, my total area is going to be kind of small here, isn't it? Because this was positive displacement, this was negative displacement. My net displacement, probably still a little bit positive. You know, that looks like that's a little bigger area. See how that works? Isn't that cool? That's great. Okay, so anyway, if we go back to this idea of a mean value theorem, though, look what we did here. Oh, wrong way. Yeah. Oh, it's down here. There we go. Okay, so here's my pretty boring trip, just constant acceleration. Start at, say, 0, and let's just say that when I get up to this spot right here, I'm going 100 miles an hour right there. Okay. So let's just look at that area under that curve. Right, that's the displacement I would have, starting at 0, accelerating, and we don't know what the rate of the acceleration is. But anyway, we know that at the end of this thing, my final speed is 100, right? What's another way that I could accomplish the very same displacement in the same time period? Yeah, what if I just put my cruise on 50 the whole time? Does that make sense? Right? Yeah, because if I grind down the area under this curve, this is a pretty simple one. This part right here is just going to fill in that part down there. See how that works? And so the mean value, the average value of this function, in this case, is pretty obviously 50, which makes sense. It's halfway between 0 and 100. But that's only because this was such a simple curve, right? Because it just happened to be linear. If it hadn't been linear, would it have had to have been right in the middle of my starting and ending value of the function? Not necessarily, right? Does that make sense? Okay. I just chose an example where it was really simple and linear. But this one back here that we looked at before, well, whoops, getting lost. This one, you know, being as this isn't linear, we don't know where the midpoint's going to be there. It depends on what this area under the curve is, right? And we get that from calculus. Okay, make sense? So here's the mean value theorem then. Honestly, the way that we use the mean value theorem the most, what we're really looking for typically, is the mean value, the average value of a function. And so really a better way to write this thing, a better expression of the mean value theorem, would be to solve for that. So the average value or the mean value of a function on an interval just equals the area under the curve on our interval divided by the width of the interval, right? Okay, so we're just going to choose to express this as a rectangular area. And would you agree for any rectangle, area divided by width equals height? Isn't that great? Okay. Well, might as well try a problem. It means we don't really have time left to go to the lab. Let's look at a practice problem that uses mean value theorem. Okay. Okay, something like this. Oh, and of course the way the mean value theorem, it's kind of cryptic like most things in calculus, and what they actually say about this is that in the mean value theorem, if f is defined on some closed interval from a to b, then there exists some number c such that this is true. So in other words, there has to be at least one place between A and B, call it C, where the function has its own average value. Okay. And so if we look at our speed example, somewhere between 0 and let's just say this was 10 seconds, there has to be at least one place if the average value of the function was 50 and our function was smooth, right? If it didn't jump around and have holes in the function, there obviously has to be at least some place between that point and the other end of this interval where the function has its own mean value. Okay, so that's how the calculus defines it, but in practical terms, we don't often use it that way. Here's the kind of questions you're going to answer, though. Stuff like this. Something like that. Find C and f of C. So we want the average value of the function on this interval and the x values where the function has those average values. Where does it actually cross its own average value? So how are we going to do this? What's the calculus look like? All right, to find f of C, what would we do? See if you can remember. How's the average value of the function defined? And so the average value is going to be the total area divided by, by the width. Right, good, exactly. So it's going to be, weird. Ran out of ink, I guess. So area from 0 to 2 divided by 2 minus 0. And we can just plug in the specifics, right? That just becomes an integral that we can do. So we get the definite integral of x minus 2 times the square root of x from 0 to 2. And instead of writing it in that cumbersome way, dividing the whole thing by 2, let's just put a 1/2 out there. Okay? So what's that look like? What's the antiderivative? We can. Good. Okay. Well, now we just flip into calculus mode, right? Antiderivative of x is x squared over 2. Now, how are we going to deal with the square root of x again? Okay, 1/2 power. So we'll rewrite that as x to the 1/2. And then what's going to be the antiderivative of x to the positive 1/2? Good. Good. We're going to add 1. Good. So we get x to the 3/2. Okay, times 2/3. We already have a 2 there. So times 4/3. Okay. Agree? Okay. And remember here, I don't want to make this confusing. And so if this doesn't help you, just block this out. But we have the option here. When we're evaluating our antiderivative over these limits, we have the option of chunking it in one big group like we did in that first example, right? So we can take all this stuff evaluated at 2 minus all that stuff evaluated at 0. Or we can chunk it term by term, right? We could take this first term evaluated from 2 to 0 minus the second term evaluated from 2 to 0. Now in this case though, I want you to look ahead a little bit. That 0 is kind of important. Why?
Because it's going to be 0.
Everything's going to go away at 0, isn't it?
Yeah.
Right? each of the terms has an x in it. And so when x is 0, everything goes away anyway. And so we don't even need to give this one a lot of thought. This time we just get the answer 1/2 times all this stuff evaluated at 2. Because I'm just going to subtract 0 from that anyway. Does that make sense? Okay. Okay, so that's our answer. It's kind of messy. Let's see, 2 squared, so that's just going to give you 2, isn't it? And 2 to the 3/2 is just ugly. 2 to the 3/2 is just the square root of 2 cubed. Okay, so that's f of c. Now the question is, what's c? Well, gosh, that's going to be kind of not a fun one to solve. But if I want to actually solve for where is the x value, where the function has that value, that's the average value of the function. How would I find that? There's the function. If I want to find the places on the function where x, I want to find the x values where the function, the y value is that, what would I do? That's it. Exactly. This becomes just an algebra problem then. I'm just going to take this ugly answer, take that whole big ugly answer, and plug it in for f of x, right? And we want to just ask the questions then, what are the values of x where the function is that? And that's going to be kind of an ugly equation. So we get 1/2 times this whole thing here. We're probably not going to have time to finish this, but where that number equals x minus what is it, square root of, what was it? 2 times the square root of x. Okay, and I'd have to solve that equation then for x. That's kind of a nasty one to do. We're not going to have time to finish this. Can anybody tell me what would we do? How would I solve? That's a radical equation. I don't mean a radical equation. I mean it's an equation involving a radical. So how do we solve an equation involving a radical like that? What is it? TI-89. Well, good answer, but the batteries are dead. Now what do you do?
Buy more.
Yeah, buy more. Okay, touche. You see, there's a real simple. I'm not saying that the job is going to be simple to do, but there's a simple approach to solving equations involving square roots. Okay, but you got to isolate the radical first and then square everything, right? And this is going to be an ugly one. There's no doubt about it. So we'd have to get this. We'd have to get that. I think it's probably, I picked what it was supposed to be a graphing calculator one, I think. But, I mean, we won't finish it. But you get the idea. We'd have to get that square root by itself on one side of the equation. On the other side, I'm going to get this great big mess. If I square both sides, on the other side, it's going to boil down to something like this. It's going to boil down to, on this side, I'm just going to get, I'm just going to get x. On the other side, I'm going to get x minus some number, call it c, equals 2 times the square root of x. Agreed? And so if I square both sides, over here I'm just going to get something I can expand out. I'm just going to get x minus c quantity squared, which I can do. It's ugly. On this side over here, I'm just going to get 4x. Now I can combine all that into one big quadratic equation and solve it and get some answers. That doesn't sound like a lot of fun, but that's how we could do it, right? Okay? Kind of a challenge. Wish I had more time. Now that's a little bit of a challenge.
Yeah.